Start with what we know, a single point charge. If we bring in a second, opposite charge nearby, we create a standard electric dipole. Now, let's take two of these dipoles and squish them together end to end. The two positive charges merge in the center, leaving us with a minus Q, a plus 2Q, and another minus Q. This specific layout is called a linear quadrupole. By stacking charges this way, they partially cancel each other out. The resulting electric field behaves very differently as you move further away, which leads us to the main derivation we need to solve today. Take a look at this hand-drawn diagram. We have our three charges sitting at points A, C, and B. Way off to the right, we have point P. This is where we want to measure the total electric field. To do that, we need our distances. The distance from the center point C to P is R. The gap between our local charges is A. That means the closest charge at point B is R minus A away from P, and the furthest charge at point A is R plus A away. Next, check the vectors at point P. The two negative outer charges pull to the left, generating vectors EA and EB. The central plus 2Q charge pushes to the right, generating vector EC. Mapping these exact distances in push-pull directions is the single most important step. If you get this specific diagram right, the rest is just algebra. Here is our starting equation for the net electric field. We add the two leftward poles, EA and EB, and subtract the rightward push, EC. Then we substitute in the standard KQ over distance squared formula for each term, using those distances we just mapped. To combine these three fractions, we need a common denominator. We multiply the bottoms together to get this massive block. R squared minus A squared, all squared, times R squared. Doing that forces us to cross-multiply the numerators, which leaves us with a huge, messy polynomial expansion trapped inside these brackets. Once you multiply all those terms out and cancel everything that overlaps, the entire top bracket collapses down to a much cleaner expression, 6a squared r squared minus 2a to the fourth. If that algebra felt like a lot, don't worry. Expanding those polynomials is the most tedious mechanical part of studying quadrupoles. You have now successfully cleared the hardest hurdle. Now we apply the far field condition. This notation, r is much greater than a, means point P is so far away that the tiny gap between the local charges becomes almost invisible. Pause the video right here. Look at the fraction above. If a is incredibly small compared to r, what terms can you confidently throw away? Give it a try. Because a is so small, anytime it's subtracted from a huge r term, it barely makes a dent. So we drop a from the denominator entirely, and we drop the tiny 2a to the fourth term from the top, leaving us with this simplified ratio. Cancel the remaining r terms from top and bottom, and we get our final result. The electric field is proportional to 1 over r to the fourth. At immense distances, a quadrupole's electric field drops off incredibly fast. It fades out much quicker than the fields from simpler charge structures. Now let's look at the math for electric potential, which you can see at the top of this second page. We set up our equation by adding the potentials from all three individual charges. Because potential is a scalar quantity, we don't have to resolve left or right vectors. We add terms directly using their native positive or negative signs. This makes finding a common denominator less punishing, bringing us cleanly to this middle fraction. We apply that exact same far field limit, dropping the small a term from the denominator, and the result simplifies instantly. The total potential is proportional to 1 over r cubed. The scalar math required fewer steps, but the result is similar, a highly accelerated rate of decay over distance for the potential. Let's look at this summary chart to see how all these pieces fit together. For a single point charge, potential drops by 1 over r, and the field drops by 1 over r squared. When we pair two opposite charges into a dipole, they begin to cancel each other. The formulas shift. Potential decays faster at 1 over r squared, and the field drops at 1 over r cubed. And finally, our quadrupole. By perfectly balancing two dipoles against each other, the decay is even faster. 1 over r cubed for potential, and 1 over r to the fourth for the field. Every time you add symmetry and balance to a group of charges, their distant electrical reach decays exactly 1 power of r faster. Take a screenshot of this table right now. It's the perfect study guide to keep these rules straight.